Hey everyone, thanks a lot for sticking with me during the last talk. Yeah, I know it's been a long day, but yeah, I appreciate you staying here. My name is Pavlo. I will be talking today about some advanced techniques for building Kotlin DSLs. And before that, just a few words about me. So I am Google Developer Expert for Android, and I also work on mobile infrastructure at Lyft. And now let's talk about the agenda for this talk, and let's see what we will be talking about. So overall, the presentation will be a bit filled with the code. However, all the source code will be available is available on GitHub. Yeah, so don't worry if you will not get something through the slides. There will be opportunity to check it later. Just like I want just to share a main idea of the Kotlin DSLs and how to make them pretty interesting and using some advanced techniques. So basically here in this talk, we will take a look at some concrete examples of a Kotlin DSL because in my opinion, it's not enough just to go through some syntactic elements of Kotlin and just take a look at them in some abstract situations. I think more convenient and more clear will be just to combine everything that Kotlin provides to us and just see how it serves some specific purpose and see some learnings that we can get from it. And once we will take a look at the example of this DSL, we will just decompose it into some small components and see how actually Kotlin can help us to achieve the purpose of the DSL. Okay, so the example of the DSL. Our DSL is used as a Starlark code generator. So don't be scared of the word Starlark. Basically, this is a programming language which is a Python dialect. So if you're not familiar with Starlark, this is a programming language that is used as a configuration language for a Bazel build system. So for example, in Gradle, we are using Groovy or Kotlin scripts, and the same way Bazel uses Starlark. So throughout this presentation, if you will see any code snippets that say Starlark code, let's just assume that we are taking a look at some Python code because in this context, they'll be completely the same. Yeah, and you might ask, okay, so if we are writing a code generator, so how does the DSL can help here? The purpose of this DSL is actually to replicate a Starlark syntax in Kotlin. So basically, we will be writing a DSL that looks like the same or like tends to look the same or as close as possible to the actual Starlark code. And later, I will show the concrete examples of how it works. Yeah, so if you are interested to see like it in more details, it's available on GitHub in the project Iron. Yeah, so overall, this project is about some automated migration from Gradle to Bazel. Yeah, so if you want to be aware, like have more idea about how it is used for the migration, you can check some of my recent talks at BazelCon about this. Okay, so Starlark code generator. So let's see, we have this snippet of Starlark code. And again, let's just assume that this is a Python code. So here we are having some variable that we assign, like we have some list. And then we have this Android binary. So in this context, this is just a call of a function. And basically, just for context, in Bazel, this function will create a target that will make our application buildable and will be able us to build and launch the Android application. So in order to write a DSL for it, we will do something similar. So here is the Kotlin code. So just like for a second, I will go back to the Starlark code. And now we go back again to the Kotlin code. And as we can see, they look and feel like kind of really similar or almost the same. Of course, we're not able to like make them completely the same because we'll still have some limits in terms of DSL functionality, but we can make it pretty close. So basically, with the DSL, we can just define content of the file that we need to generate in Starlark. And for example, then we can write this file in the separate variable. And then below, we can just write this file to a file system. Yeah, and basically, overall, what does this DSL do under the hood? It does a pretty similar thing that actual interpreter of a Starlark language does, or maybe like interpreter of any programming language does. At some point, it arranges every component of the code that we wrote into some tree data structure, which we call abstract syntax tree. So if you can see that basically we can split all the code into some small components, and then we arrange them into some form and shape. So basically, when we are talking in terms of Starlark interpreter itself, the like original one, it will then use this abstract syntax tree to actually execute the code. However, for our DSL, we will also build the same tree, but we will use it to actually generate the real Starlark code and make it introduce all the indentations, formatting, and stuff like that, which makes development and reading the code pretty easy. So okay, what is this tree consist of? Basically, first, like node, we have, for example, we have our function call, which is Android binary, and for that we have a like separate tree node, which we'll call function call, and its specific instance is Android binary. Then this function call have a name. So for name, we will have another node in our tree. And for the value, we will have, obviously, another node. Similarly, we can do for manifest, like another argument which is called manifest, and its value like Android manifest.xml. And also, we can have a slightly more complex cases. So here in the sources, we have an argument which is called sources, but its value actually is a result of a concatenation or binary expression with the operator plus. So here we will create another like tree node for this binary expression, which will have left operand and right operand present. Yeah. So basically, this is what our DSL will do. It will first like create this abstract syntax tree and then generate some code based on this tree. And if we're speaking about the code, so each node of that tree will be represented by a separate class in Kotlin. So for example, we have a root tree node, which is a Starlark file, and we can see it consists of a list of statements, which are also nodes. Then we have a function call node, again, another tree node that stores information about the function, and also it has a list of its arguments. So for argument, we have another node, and so on and so forth. So basically, every Starlark language component and like part of the syntax is represented by a specific tree node and like arranges everything into some specific form and shape in terms of a tree data structure. Okay, so now that we saw like a brief intro to the overall what our DSL will look like, let's decompose everything that it consists of, and let's see how individual Kotlin features can help us to achieve similarity with this or that parts of a Starlark language, so that we can make our DSL look and feel like the actually Starlark language. So yeah, in order to start working with DSL, we need to make sure that everything that we wrote for our DSL is not available everywhere, but it's available only at some point. So basically here, we can have a build.bazel function, and basically inside the curly braces, we will write our DSL. So you might ask, what is the weird name like build.bazel? But basically, this is the name of the Starlark file that will include the code. Basically, since Starlark is a language for Bazel, so its files, majority of its files are called build.bazel. So basically, we then can have a similar function that will identify that we now are writing the content of this file. And then once the function is executed, we'll just write this file to the file system. And you might notice that this function has a weird name because it has like consists of two words separated with a dot, right, with a period. So basically, this was done just to replicate exactly the name of the file, and it can also be done like, for example, myfile.py if you're speaking about Python. But basically, in order to do this, we can do some pretty interesting thing. We can just create a dummy object in Kotlin, which is called build, and then we can just define an extension function on this build function, which is called Bazel. And basically, this is how we'll be able to have this function that consists of two names. And the most important part here is this body of this function. Basically, this is where our curly braces start acting. And basically, the type of the argument is lambda, and it's not just a simple lambda, it's lambda with a receiver, where receiver is this Starlark file context file. And basically, this is the class, that enables all the functionality of our DSL. So when we get back to the DSL, we have this, after build.bazel, we have those curly brackets, and usually IntelliJ IDEA will show us a hint that in this case, we are kind of inside of the context of Starlark file context file, and everything that is every property, every function, and every extension function defined there, we'll be able to use them inside of these curly brackets, like first-party citizens. So for example, if we have this Android binary function defined in the Starlark file context, this means that inside of this DSL context, we'll be able just to use this function like a top-level function without any prefix. Okay, so yeah, and just some more details about this Starlark file context file. It will basically contain some different components of the DSL, as well as a list data structure called statements, which is basically another storage for 3 nodes, because basically whatever functions and DSL components we use, their main purpose are to create different types of those 3 nodes and put them into the right place so that we can create this 3 data structure. Okay, so let's start from the first component of our DSL. This one will be pretty trivial because, for example, what if we need to generate a function call in Starlark? As we know, the way we call functions, it's pretty similar to the way between Kotlin and Python. So basically, at the top, you can see the Python code, or Starlark code, and at the bottom, you can see that our DSL that replicates this syntax. Yeah, as you can see, it's pretty simple. And basically, we are just implementing here an Android binary function. So we are implementing it as an extension function for the Starlark file context, just to make sure it's available inside of our DSL context. Yeah, it takes some arguments. We can default some by null. And yeah, the core thing here is that we are creating those argument objects, which again, if you remember from the previous slides, they are 3 nodes. And then we have basically the argument, and for each of the values that we pass for those arguments, we also wrap them with other 3 nodes. So for string, it will be string literal, for list, it will be list expression, and so on and so forth. Then when we collected all those arguments, we pass them to another 3 node, which is function call, and then we just put this function call to the list of statements that we defined earlier in this context, Starlark file context file. Yeah, so might be a bit confusing because a lot of nodes and classes, but basically the idea is that we are taking some arguments in this function and we are creating basically a subtree from this data and adding it to our main tree that we are building. And okay, so functions were pretty simple, but also Kotlin has another interesting feature, which is indexed access operator. So if you use Kotlin, you most probably used you tried to get some items from the list by index. And when you are using those square brackets to get by index, you used this indexed access operator. And we can use it for our purposes for building DSL. So let's imagine we just need to generate simple expression in Starlark, which just creates a list of integers. So our DSL for this will look like this. Pretty similar. We're again using those square brackets, but unfortunately in Kotlin, square brackets cannot be used without anything, so we need to apply it to something. And for example, we can create a keyword called list for our purposes, and basically this will allow us to use those square brackets. And basically the way how it works, we need to kind of create this new operator in our DSL. And what we can do, we can just create a simple property inside our Starlark file context file class, sorry. And basically it will reference another object, which is also like a dummy object, to which basically then when we have this object, we can overload an operator, which is called get. and make it an extension function to this builder object. And basically this get operator, it's something that represents those square brackets in Kotlin. So we can here pass a variable list of arguments as an argument. And again, we are creating another tree node, which is list expression. And we are putting there all the elements that we passed. Yeah, and again, this way we will be able to use this keyword list. Yeah, and this is just like really like a keyword and on which we will use those square brackets. Okay, next interesting thing in Kotlin is a property delegation. So everybody may be familiar with that when we're using this keyword called by. So let's see how it can be leveraged in our DSL. So let's take a look at another use case. We need to generate some code which assigns some variables with some values. So we have string value, we have list value, and we have dictionary value. How can we replicate some syntactic elements in Kotlin? We can do it this way. So basically, we are also creating variables, but for some reason, we are using by operator, and let's take a look why do we need to use it. So first, we are defining those variables as val, or we can use var if we want to reassign them in future. It's also possible. So this is just to be able to use this variable somewhere in future. For example, we can define this variable, and then we can use it inside of the function, and we can pass it as an argument. So by having reference to it, we'll be able to actually do it. But what about by operator? Why don't we just use a regular assignment operator, like as in Kotlin when we are assigning values to our variables? The problem here is that if we use just simple assignment operator, basically what it will do, it will only assign the value to the variable. But this is not something we want to do. What we want to do is we want to generate this assignment statement in Starlark. So we need to preserve this information about the moment when this assignment happened. And that's why we can use by operator, and under the hood, we can implement the functionality that we need. And what's also important is that the actual type of those variables, like my string, my list, will be represented by also another nodes of our tree. And as you can see, we have string reference, list reference, dictionary reference. Basically, they are all preserve the type of the variable. And we will now see why the type matters. So basically, here is the classes that represents those three nodes for the references, for the variables that we are assigning. As we can see, this list reference implements a list interface. And why is it important? Because if you remember our functions, they have some types for the arguments. And for example, when we use function, we can always pass some value, like string value or like list value. But sometimes, and pretty often, we will need to pass some reference to the variable, which we defined above. And I mean, in Starlark, it's a pretty common thing. So this way we'll be able to do it. Basically, we can pass this list reference to somewhere where only list is expected. The same with dictionaries. So basically, it's map in Kotlin. And we would want to do the same with strings, but here's the catch. The class string is final. Basically, we cannot extend it, and we cannot do it the same way. However, what we can do a pretty simple trick. We can use not string, but we can use char sequence. Basically, char sequence is an interface that string class implements. And for the purpose of DSL, I think it will be pretty sufficient just to have a char sequence. And now what we can do actually, the use case I just described. So what if we need to generate something that consists of two parts. So first, we need to generate some assignments, because I mean, this is simple cases, but maybe we are taking this data from some other places. It depends on context. But basically, the main thing here is that then we are passing those name, src, and manifest values as arguments to the function. But the function expects some specific types, like list or strings, and this way we will preserve the type safety. And this is actually a very powerful feature of this DSL particular, that it preserves the type safety of everything that we are doing. So we're not able to pass list somewhere where string, for example, in Starlark is expected. And the only change in the Android binary function would be just to replace all the occurrences of string to char sequence, and we are good to go. Okay, so now we've taken a look at some components of our DSL, pretty simple ones, but let's add some customization to our DSL, because users want as more and like as much customizability and extendability as possible in order to be able to adjust to their use cases. And let's see how it can be achieved with some other cool Kotlin features. So let's imagine the case. We want to generate an Android binary function call, but here's the catch. The developer of this function, or this library, basically it's a standard library, Starlark, or like whatever any case. For example, they introduced a new argument to the existing function, and for some reason, the DSL was not updated yet. And basically, in this case, we are not able to generate this some new argument because our DSL does not know anything about that. But still, we want to provide our users ability to be more flexible and still somehow overcome this obstacle. So what we can do? We can go with the following approach. So first of all, if you notice, our function call for the Android binary has a slight change. So before we used round brackets in our DSL, but now we can use curly brackets, and add some magic to our DSL. So basically, this outstanding argument that is not present in our DSL yet, we can just define it with a string, because we need to assign some value to it, and we need to know the name of this argument. And then we're using some weird assignment operator, but with some like slight changes, which lie in the fact that we're using assignment operator with backticks. So basically, the approach here again is pretty similar to what we already had with build.bazel, where we're actually creating a new context object, and this context object will provide some functionality for our DSL that is scoped only to this function call. So how does it look like? So inside of this context, similarly to the way we had a list of statements that collect 3 nodes, here we'll have like a list of arguments that we are using, and then we will define a list of like specific arguments that this function provides. So for example, this function can have like 20 arguments in general, and we can select which ones we will pass. And to make sure that when somebody assigns value to the name, for example, and this value will be automatically stored in the args, in the list of arguments, we can just do some simple property delegation, and it will be handled under the hood. And basically, this by operator, we can overload it because Kotlin allows us, again, to overload this property delegation stuff. And yeah, basically what we are doing here under the hood is pretty simple. Whenever somebody writes something to the name, for example, right, we just like wrap the value in the argument, which is a 3 node, and then put it to the list of arguments. But then here's the most interesting thing, like how do we implement this assignment operator? So in Kotlin, there is a pretty neat feature where if you're using those backticks, like kind of quotes, but weird quotes, you can name your functions almost like whatever you want. And in this case, we can just like name our function with the assignment operator. And this will be actually just a simple extension function to the string type. Why string? Because we are defining the name of our argument, of our custom argument with a string. And we're just making this function as an infix function because we need to make sure we don't call this function with dot, but we just like place its 2 operands around it. So one on the left and another one on the right. And we're doing the same thing. We wrap everything with an argument. Yeah, so here, like, don't be scared of this expression stuff. This is basically another function. Basically, to avoiding some too much details, it just takes the value that we passed to this assignment operator, and it wraps it with a 3 node if it's not wrapped yet. But if it's already a 3 node, for example, if you're passing not the value but some reference, like from the variable that we defined earlier, so we'll just use that node. But basically, we're just like wrapping it as with a 3 node. Okay, so we can somehow deal with custom arguments, but let's consider another case. What if the library developer adds some new function that is not present in our DSL. So we can also have something similar. So basically, we can define the name of our function with a string, and then use curly braces again, and do the same thing with a custom argument assignment. And the way how we do it is pretty simple. This string, it will be the function name, and like we are overloading the operator, which is invoke. Basically, this is the function call operator, and we are making it as an extension function to string. So basically, this is how we achieve those curly braces after the string. And the body is pretty the same. So basically, another type of context, similarly as we done before with build.bazel, for example. Yeah, so we're just creating context class and wrapping everything with another type of a tree node and adding it to statements. Okay, so we've seen some like basic elements of a DSL. Now let's take a look how they can be combined into some more complex cases. For example, let's say we have this Starlark code, which now is a bit more complex in a way that it uses a plus operator, basically concatenation. So we are not just passing some value, but we are composing this value from two items. And what we need to do, we need to actually generate this plus operator. And we can do similar thing with a DSL. So again, as we saw before, we are defining a variable, which is called source files. It's a list variable. And then we are calling Android binary function. And again, we are using this, our custom plus operator, but with those backticks. So the approach here is the same as it was before. And again, why we are not using just a regular plus operator, but with those backticks? For the same reason, because if you use just a plus operator, it will compute this concatenation on the Kotlin level. And in Starlark, we will have no idea that we need to generate this plus. So yeah, this is why we are doing it. Yeah, and here is the same thing. We are implementing this plus as a function, extension function to an existing type. So for list, it will be like extension time for list, and like we will have duplicate of this function for each type. And the main thing is that we have a list binary operation, which again is another node of the tree, which has left and right operator, which then it adds to the tree that we're already creating. And yeah, another thing is that this binary operation itself is a list. It implements a list interface, and this is how we are passing the result of this plus operation to the function which expects just a list. So yeah, again, we are preserving type safety. Yeah, so and here we can consider another case. So as you remember, we just recently discussed that we can have our custom arguments in the functions, and we have those assignment operators with backticks. So in the first case, we're using just regular assignment operator in the first Android binary call. And in the second Android binary call, we're using this like custom argument, dynamic argument and this operator, our custom operator. And the catch here is that the order of operations when Kotlin executes the code is different. So in first case, the first function that will be executed and like ran by Kotlin is a plus. So basically, first it will evaluate the result of source files plus list, even if it's our custom function, so it will run it. And then it will assign this value to sources. However, in the second value, since the assignment operator is not a Kotlin operator, but our custom function, the order of operations will be different. And this is also a catch. So when you're writing the DSL, it's important to understand the order of operations. And basically for those two cases, the implementation of a plus operator will be different just because of the order of the values. Because in the second case, we will just assign the source files value to the SRCs, and we'll disregard the second something to the right of the plus operator. And how we can do it? So basically, we can get back to our assignment operation with the backticks, and we can modify it. So now it will return something which is called accumulator. Basically, this is some type of object that user of our DSL will not see it. That's why we're using this underscore. But this will be actually a glue that will help us to collect everything together and not miss some values that we want to keep. So basically then we will define this plus operator as an extension function to this accumulator. And basically what it does is that it takes whatever was already written there and it replaces it with a binary plus operator, and its left operand will be assigned to the old value. And basically this way we will make sure that we evaluate this assignment for the custom arguments in a correct way. Okay, so this was about concatenations. Now let's see what problems might appear when you're writing your custom DSLs. So for example, we can have such thing as a context conflict. So if you remember, we are using those context objects to actually give some functionality, define some properties, functions, all those like assignment operators, plus operators, they are all work as members of those contexts. And basically this is how we get access to all our custom operators. And what problem can we have? So we can see we have our build.bazel function, which has Starlark file context. And we have another statement, Android binary call, and it has another context, Android binary context. And what can happen is that inside the Android binary, this like inner curly brackets, we have access to both of the context. And basically, we can do some weird stuff where basically while we are calling this function and passing arguments, we can just randomly call Android binary again, because Android binary is available from the outer context. And how do we preserve it? And how do we make sure that everything that happens inside Android binary, that we control it and we do not spill like any extra functionality that we don't need actually? So in order to achieve this goal, Kotlin standard library has something as a DSL marker. So this is annotation, which and like how to use it. We need to declare our custom annotation. For example, it will be language scope, and we will mark it with our annotation. And then we will use this annotation to mark each context that we are using. So we have many of them. Let's see, like on this example, how it works. So we marked like first context with it, second context with it, and this is basically it. So now what will happen when you will write this code in IDE? It will show you that you're writing invalid code because Android binary is something available from the outer context. But what we have done, we just made sure that we do not mix context between each other, and basically you will not be able to compile a project anymore. And this is the way how you can be flexible and make sure you do not have functionality that was not intended in the first place. However, here we might have another problem because, for example, what if inside this Android binary, when we are passing arguments, values to the argument, what if you want to use this plus operator, which is actually declared in the outer context? Because after what we have done just recently with the DSL markers, this code will not compile anymore. So what can we do here? Yeah, so basically, as you can see, with a red plus, it will not be compilable code, but we still need to have this functionality. What we can do? At this point, when we added a bunch of different operators to our DSL, it's kind of starts growing. We can restructure it and add some architecture, kind of architecture to it. So what do I mean by this? Instead of having all the functions of our DSL, all our operators, like some different operator overloads, our functions, as you remember, we defined majority of them in the Starlark file context file, basically the outer context. What we can do instead, we can separate each specific function into something like separate. For example, we can have a concatenations feature. This is the feature that implements our like plus operator. And we can have it as an interface, and we can implement all the functions that are related only to this interface. So basically, it will be functions with default implementations, since it's an interface. And then, if you want to have this concatenations feature available at some context, we can just make sure our context file will just implement this interface. And by implementing this interface, we are enabling some new feature for this context. And yeah, one more thing, we can make this interface sealed to make sure that users of our DSL will not do anything weird with that and will not implement it in their own way. And in this case, we can granularly specify that we have this plus operator, and we want to make sure it's available in both contexts, on the top level in the Starlark file context, but also when we are calling the function, like Android binary, we want to be able to use this plus inside. And we can go even further. For example, we have, let's take a look at this new argument, manifest values, which is defined as a dynamic argument. And its value like consists of key and value, because like this is a dictionary or map from Java. And as we can see, we again have this plus operator available to this dictionary context, because dictionary has its own context. But we have this operator too here. And you know that Kotlin language itself has operator too, but here it's a more like, it's a custom operator for this DSL. And we need to make sure that these two only available to some part of the DSL, but not to the entirety. And this way we can create another interface for this to operator and make sure on the dictionary context class has it. And this way we can have full controls of our features and different contexts that we're using in our DSL, and make sure we don't provide things that are not intended to use by engineers who use the DSL. And now, let's briefly also talk about some additional features. We won't be diving deeper into the implementation because overall they're pretty the same, but yeah, it's still worth considering them. So Python and Starlark have this pretty cool list comprehensions syntax operation, which is basically a builder, pretty concise builder for the list. So for example, here we are defining a sources variable. And basically for each file in the list, we have a list of strings, right? Main activity, for example. For each string in this list, we will modify the string, for example, and add .java extension so that we make sure that it's actually a file. And then we're just passing this value to the Android binary. So yeah, we can do something similar in Kotlin, basically with using different named operations like, so the logic of the implementation will be pretty similar, but this is how we can combine everything together. So again, for each file in the list of strings, we are doing some operation, which is basically adding some extension to the string. And what's important here also is that it will have type of char sequence or strings, because it will figure out that we are using a list of strings, that then the element of the iteration will be just a string. And then we are assigning everything to a sources variable, and we also will keep the type, because we know that list comprehensions can create list. So basically they are of type list, and this is the way how we can pass it as an argument to an Android binary, for example. And also I would like to talk briefly about some new modern stuff that we have in Kotlin community, like content symbol processing. And let's consider how it will help us to make the development and maintenance of our specific DSL a bit easier. So as you remember, we have these DSL functions like Android binary that we can call. And let's take a look at the full implementation of this function, because in Starlark it has many arguments, and basically we need to define everything by hand. However, we need to also define it twice, because we have one function with round brackets and another one with curly brackets, and we use different approach for them. So it doesn't matter what exactly code is written here, but we just need to make sure, just to see how much code we have. And moreover, we can have even hundreds of those functions, because there are a lot of them, and we can even have some custom ones. So instead of like writing everything like this by hands, we can a bit automate our life. Instead, we can have a simple processor, basically an annotation processor, that will generate all the boilerplate for us, like with no effort. So the idea here is the following. For each function, we will have an interface. For example, in this case, it's Android binary because our function is called Android binary. And each property of this interface will represent the argument. And its type will also represent the argument. And the key point here is that we're using this library function interface. And basically, this is the way how our simple processor will know it needs to generate some code. Yeah, so we will not consider like the details of the simple processor because yeah, it's topic for another discussion. But yeah, overall, this is what can be done. Yeah, if you want to have an idea about how to write such a simple processor, you can go to the Medium article, and basically it describes pretty similar simple processor that we've just discussed. Yeah, and just final thoughts on that, how all of this looks in practice. So here is a more like a wildlife example of what Starlark can look like in some cases. A lot of code, just briefly we'll go through it. So we have a list comprehension, and for each item in the list, we are calling a function which is called general. Then we are using this file element, which is like item of the list. Then we're using this plus operator. Then we can use slicing operator from Python or Starlark. We haven't discussed it, but yeah, basically it can be implemented pretty similarly. And yeah, so here is how the DSL for it looks like. Yeah, so pretty much the same. We have the concatenate list comprehension that we discussed, and for each file in the list, we will call the function. We will again use file as some iteration like representative, then plus operator. Then for slices operator, we're using Kotlin range operator. You can also overload them and like add some new functionality, and looks pretty similar. And yeah, that's basically it. So to conclude everything, yeah, I know that like it's pretty a lot of code, but my main idea here is that in order to build DSL, we can actually use some different Kotlin syntax elements for some non-conventional cases, and in the ways that they are not intended. But I think this is fine, and like unless you experiment and like trying to adapt and adjust the DSL for use cases, if like any operator works for that, yeah, I think this is cool. It's fine to apply it this way. So yeah, again, all the source code is available on GitHub. And yeah, thanks a lot for watching, and thank you with me for sticking with me in the last talk. Yeah, and thanks also Shalom and Ryan for having me. Yeah, thanks a lot.
Great. Thanks, Pavlo. All right. Wow, that gave me flashbacks to doing compiler development.
Yeah, that has a bit of that flavor.
I should have expected that because domain-specific language, but
yeah, this is a specific case for building language. Yeah, so it has a bit some of a domain. Yeah. Yeah, so I think I will go through questions in Q&A section.
Sure, yeah.
Yeah, is it possible to use Kotlin DSL to replicate Java in Kotlin? Asking for a friend.
Basically just a joke question.
Yeah, but I think this is a valid question. So with Java, it will be, I think, more complex. It depends on the actual language, because, for example, if you want to replicate Lambda expressions and some newer features from Java, yeah, so it definitely is possible to do, I think, in some way. I haven't tried, yeah, but it would be nice to just to think about it, and yeah. But in general, Kotlin still has some limitations, and for some Starlark use cases, they're pretty similar in terms of load and the syntax. So yeah, I think in terms of Starlark and Bazel use cases, it will be a bit easier than for Java, definitely.
What I was thinking is like you could get all of the deficits of the Java programming language and like none of the benefits of skipping the Kotlin compile time process. So it's a terrible idea.
Yeah, I mean that sounds pretty fun. So it's a cool thing to try. Another question: does the advent of context receivers change how we can build Kotlin DSLs? If yes, can you explain that if it enables? Okay, so I think what it means that we have this new keyword for context, basically when we have multiple context for the same function. So we can have it as an extension function and then add some new contexts. I think basically the general idea is that when you're building the DSL and when you are implementing some part of it, you just need to think about everything that Kotlin provides. And if in this case, this is something that helps you to achieve the goal, then it's cool. From the top of my head, I don't know like in what particular cases it can be applied, but I'm sure that there might be cases where it will be applied, definitely. Okay, what might be a particular task project use case a beginner could try to get started with building a DSL? Yeah, that's also a good question. What I would say here is that definitely the important part here is that when you're building DSL, you definitely need to have a purpose for it, because building some would be able to like fulfill the like power of building DSLs.
Oh, it looks like we're having a moment of technical difficulty.
Hey, sorry, I had some out of memory on my machine.
Hey, it's all good, man.
It's broken. Sorry.
So I think where we left off is you were partway through answering what might be a practical task for a use case. So go ahead.
Yeah, sorry, I think I was talking a lot without realizing nobody hears me.
Yeah, it's all good. It happens.
Yeah, so I think the good use case might be to consider, for example, JetBrains has a pretty interesting DSL for building HTML code. So they have it in the standard library. Yeah, if, for example, if you want just to figure out like how these things work, you might want to try to replicate it. And also you have already source code available in the standard library. You can just check like those ideas that you might have. Yeah, so, but overall, like if you have like any use case where you think it might be suitable, yeah, just feel free to try. I think the best thing is when you're doing it for some specific purpose, like that solves some of your problems. I think in this case, you'll have the most of a motivation to do it. Yeah, I hope it answers the question. Yeah, do you test DSL implementations? That's a pretty interesting question, and the answer is yes. And when writing this specific DSL, I had a use case. I wrote such tests that I've never used before. So, for example, my tests were to check the syntax of a DSL because we're replicating the language and make sure it compiles. So, for example, many times you have a lot of these context objects that overlap constantly. You're trying to like put everything through different interfaces, and sometimes in some like third level depth of the context, you're trying to use operator, and some other change that you've made recently change your DSL so that this particular operator is not compilable because Kotlin then complains that you don't have some types matching, some generics, some other stuff. So basically, everything that I wrote in this slide, I had tests that just sit there, have this code, and make sure that it's compilable, because like anything can change. But yeah, overall, it's usually it's better to test everything, and DSLs are not exceptions. Yeah, I think that was the last question.
That's it. All right. Well, just one more time, thank you so much for the talk, Pavlo. Much appreciated.
Thank you so much for having me.
And on behalf of myself, I would like to thank FaZe and Shalom for continuing to put on Android Worldwide. And I think I probably speak for most of the people participating and facilitating Android Worldwide, and thanking everyone for joining and watching and sharing on social media the talks and clips and all that kind of stuff. So yeah, that's basically it. Thank you so much, everyone. Yeah, and we'll see you in something like 2.5 months. All right. Take care, everybody.